Chapter 4. Section 1 of Chapter 4 is going to talk about the atomic model that we know today. So Chapter 3, we learn Dalton's atomic model. Remember John Dalton. And this chapter, our objectives are, 1, explain the mathematical relationship among the speed, wavelength, and frequency of electromagnetic radiation. We'll also learn what electromagnetic radiation is, obviously. The second one, discuss the dual wave-particle nature of light. Dual means two, and so we're going to talk about light's way it behaves like a wave and how it behaves like a particle. The third one is discuss the significance of the photoelectric effect and the line emission spectrum of hydrogen to the development of the atomic model. And then finally, describe the Bohr model of the hydrogen atom. So with the electromagnetic spectrum and the line emission spectrums, we're going to talk about what the electrons have to do with that. So, properties of light. We need to understand what is happening with light and what light is in order for us to understand what the electron's contribution to that is. So, electromagnetic radiation is defined as the form of energy that exhibits wave-like behavior as it travels through space. So you know of electromagnetic radiation every day when you turn the lights on. Visible light is part of the electromagnetic radiation spectrum. So that's the spectrum in the next section, or next term there. All the forms of electromagnetic radiation form this spectrum. When you have a rainbow, you are seeing visible light split up into the different spectrums of the visible light, of white light. So, for the electromagnetic spectrum, we have up here gamma rays, which are high energy rays that can cause great damage. That's part of like nuclear explosions, nuclear radiation that we talk about when you have the maximum damage done. Gamma rays are those. Then we have X-rays right here. X-rays are also a form of radiation in this spectrum, and we try to limit what we're exposed to of X-rays, and that's why they'll put the lead vest on you over different, especially your reproductive parts, because you don't want any exposure of X-rays to your reproductive parts, because we don't want children with 3 arms. You know, normally we want children with 2 arms, and too many X-rays can cause damage to your egg and sperm. So we try to avoid that at all costs, so you only get X-rays when you need them. Then ultraviolet is on the spectrum. Right in this region, you can see wavelengths here, and then visible light is right between here, this spectrum of wavelengths of this size, and then infrared. Now we know infrared, we have infrared cameras that we use at night, and that helps us see at night. Then you have your microwaves down here. When microwaves first came out, like my grandma was scared for us to stand by the microwave because radiation was so unknown and people didn't know about it. And now we've almost become too immune to thinking about it. And it's kind of swaying back to that spectrum where people are thinking about the dangers of these radiation types. So microwaves fit on this side of the spectrum, on the other side of visible light from X-rays. Then TV and FM radio waves, that's how we get our radio, that's how you get your signal, is this wavelength of light up here. Then you have your AM radio waves are farther on this spectrum, and then you have long radio waves. So if you've ever listened to AM radio, it doesn't come in as well. And FM radio waves are a little bit of a different wavelength, and so they come in better. But that's the spectrum. And that's what electromagnetic radiation is all of these energy forms in the form of waves, and light waves being in the light that we see as visible light being in that wavelength. So, the electromagnetic spectrum, I'm going to skip that visual concept, it just repeats what I'm going to say here. Properties of light. A wavelength is just that, the length of the wave. So it's the distance between corresponding points on adjacent waves. Adjacent means next to each other. So you take it from peak of one wave to the peak of another. You just go from the same point on one to the same point on the other, and that's the distance. Frequency, however, is defined as the number of waves that will pass a given point in a specific time. It's usually the time period of 1 second. And we'll work more with frequency and wavelength in class. We'll do some PowerPoint, interactive PowerPoints or interactive smartboard activities with this. But frequency, so has a time period in it. It's the rate. Okay, so frequency has a time period and wavelength is just a distance. So we have a connection between the two. If you have c, which stands for the speed of light, it is equal to the wavelength of that light times the frequency that it reaches or passes over through a given point. So c is the speed of light in meters per second. Wavelength would be in meters. We have to have all units matching. And then v is the frequency of the electromagnetic wave in seconds. So wavelength and frequency. So if you look at this top picture here, the wavelength is very large. In this one, the wavelength is very short. So that is the distance. So we can measure the distance they're traveling by observing how often the water level rises and falls at a given point, such as the post. So if we timed this and we counted how many waves and then divided it by those seconds, we would get a frequency. And we talk about frequency like when we are going in, tuning in our radio. So what frequency are we in? What FM frequency are we in? That's usually where you'll hear of this. So the photoelectric effect. This refers to the emission of electrons from a metal when light shines on the metal. We have talked about the characteristics of metals having luster. Luster is how shiny they are. Now, what makes them shiny are those electrons that are gaining energy when light hits it, and then they bounce off, and those are reflecting to your eyes. So when the electrons are leaving that metal and coming off, they are being emitted. That's what emission means, and that is the photoelectric effect. Photo meaning light, electricity is the flow of electrons. So when we talk about photoelectric, it's when light hits it and electrons are bounced off. So we know that there is a correspondence between these electrons and wavelengths. So the particle description of light. We talk about light in terms of particles and also in terms of waves. So we just got done talking about it in terms of waves. Now let's talk about it in terms of particles. Now that we know that electrons, when light hits the metal, electrons are shot off. We know those electrons are particles. Those particles are going to have a certain amount of energy. And so that energy is called a quantum of energy, or a little packet of energy. And there is a quantum of energy, which is the minimum quantity of energy that can be lost or gained by an atom. So when the light hits the metal atoms, each atom has an amount of energy that can be lost or gained. So quantum, it's like an amount of energy. So the photoelectric effect. If you look here, we have light hitting this metal, which is the cathode is a metal plate, and we have this stream of electrons that are going to be emitted. And you can see they're being emitted in waves. And that's your wave particle motion or wave description of motion. But now we can also describe it in terms of particle motion by finding out the electrons that are being emitted. So the German physicist Max Planck proposed the following relationship between that quantum of energy, amount of energy, and the frequency of radiation. He proposed that E equals H times V. So now V is the frequency that we had, E stands for the energy, and H then is going to be Planck's constant. Oh, let me go back. And this number is a number that you'll write on your card. You're not going to memorize that one. It's important, but you're going to write that on your card and you're going to reference that. That is Planck's constant. And by constant, we mean it never changes. It's always that number. So there's a corresponding relationship between the frequency of light and the energy that's emitted, and that correspondence is known as Planck's constant. It's always that number. And if we plug that number in, we can either solve for energy or frequency based on that. And that's, again, I think that's amazing that people can mathematically determine these things. A photon is a particle of electromagnetic radiation having zero mass and carrying a quantum of energy. So we said that there's a quantum of energy, like a little packet of energy given off when the electrons are emitted. That's called a photon. So I usually refer to it as like a little packet, a photon packet of energy being given off. And we know that you always have a full packet. There's never half a packet or a quarter, 3/4 of a packet. It's always a full packet of energy. So therefore, there is a known amount. And that is because a certain number of electrons are going to be either emitted or the electrons are going to be going to a certain level, and they always go to those levels. And that's what's going to get us into section 2 when we talk about the quantum theory of energy. So the energy of a particular photon will depend on the frequency of that radiation. So energy that photon is emitting is going to be equal to Planck's constant times the frequency. We'll just keep going. So now, the hydrogen atom line emission spectrum. Hydrogen, the reason why we talk about hydrogen so much is because hydrogen is the lightest of all of the elements. And so therefore, we can isolate that. And so hydrogen was worked with a lot, and then we could base everything off of that because we could get one atom. So the lowest energy state of an atom is called its ground state. When an electron goes to a higher energy state, it's called the excited state. That's not too hard. Those terms kind of mean what they say. Ground is you're at the lowest energy, you're at the ground. And then if you jump up, you're excited, you are higher. You're going to be at a higher energy. So don't make those terms any harder than they are. What makes an atom be at ground state or an excited state are their electrons. So what we found with hydrogen is that the investigators of the experiments showed that when electric current is passed through a vacuum tube containing just hydrogen gas at a very low pressure, they observed the emission of a characteristic pinkish glow. It always shined pink. When a narrow beam of the emitted light was shined through a prism, it was separated into 4 specific colors of a visible spectrum. So those bands of light were part of what's known as hydrogen's line emission spectrum. And it's kind of interesting if you've ever watched CSI or any of the criminal shows, they usually say the spectrophotometer showed us this, or they find out what was left at a crime scene based on their line emission spectrum. Maybe we'll have to watch a CSI episode and see that. So hydrogen's line emission spectrum is specific for hydrogen. And they found this, that you have this line that is going to be here. So excited hydrogen atoms emit a pinkish glow. When the visible portion of the emitted light is passed through the prism, it is separated into specific wavelengths or part of hydrogen's line emission spectrum. So we have this spectrum after it's passed through the prism, and it's specific to hydrogen. Other substances will have their own line emission spectrum. And that's how we can tell what was left at a crime scene. Is it really cocaine or is it just sugar? They can tell a crime and they can tell what those substances are because they'll give a certain emission. So this led to Bohr's model of the hydrogen atom. So because we had just the hydrogen atom, Niels Bohr said that hydrogen atom model is linked link the atom's electron to the photoemission. So according to the model, the electron can circle the nucleus only in allowed paths, and that's where the orbits came in. So he said the electrons are in an orbit, and when they are in that orbit, they have a certain amount of energy. When they go to a higher orbit or an orbit farther out, they have a different amount of energy. So the energy of the electron is higher when the electron is in orbits that are successively farther from the nucleus. When they go back down to the lower energy orbits, they are closer to the nucleus. That was Bohr's model. Oops, back. I want to show you. So when an electron falls to the lower energy level, a photon is emitted, and the process is called emission. When energy is added to an atom in order to move an electron from a lower energy to a higher, it's called absorption. So it either emits or absorbs. So in this picture, we are adding energy, which will make the electron go to a higher energy level, and therefore it is absorbed. When the electron, if it's out at this higher energy level up here, and we give off that energy, it is emitting energy and going down to an energy level that is closer to the nucleus. And there is the nucleus. So photon emission, and absorption. And that ends this section. Now tomorrow or Monday in class, we'll talk about, we'll have a quiz on this section. So make sure you read this section and do this lesson and answer the questions in the assignment, and then be prepared for a quiz on this section. All right.